Good afternoon, everyone. So, welcome to the third and final session of QE program on inverters. So, let me recap what we have done in last 2 days. Basically, we have covered, single phase and three phase inverters, and we have understood how to operate the inverters both in actually in various modes actually. So, the first mode is called square wave mode. So, square wave mode is a it's also called 180-degree mode of condension. It will use the maximum capacity of the inverter. So we want AC from a DC. So that is our requirement. So we will depending on the time period of the AC signal what we want, we will put full DC for half the period and full DC on the negative side for another half the period. So that is how you can use the maximum capacity of the inverter. This mode of operation is called square wave mode. So when we are operating in this mode for a three-phase half-bridge inverter, it will be also called square wave mode, six-step mode. It's called square wave mode as well. But another name of square wave mode applied on three-phase half-bridge converter is called six-step mode. It is because when you see the phase to neutral voltage of a six. This is the so this is the first thing we have seen. Then we have seen sine PWM. Then we have seen all these three techniques for a three-phase half-bridge inverter, and we have seen the fundamental is the best or the maximum in square wave mode, but it has a limitation of harmonic currents, and that's why it is used. It is not used until necessary. So if there is a limitation of DC link voltage, then we have to go for this. Otherwise, for most of the cases, this technique is preferred. So we go for SV modulation technique. If it will also help us to go to an extended linear region, which is generally offered by SPWM for another 15%. So this linear range is important because once you cross the linear range, you will enter to non-linear range and the currents will not be sinusoidal anymore. So given a inverter and a DC link, the first choice is to work on linear range. If you can work with SPWM, it's better because it is simple to implement. But if the DC link is again you are finding it less, you can go for SVM, where you can again increase the output voltage by 15%. But if you want still higher voltage, you have no choice but to go for square wave mode. But you have to live with harmonic currents and harmonic torques if you are using for induction mode. So when we are talking about three-phase half-bridge inverter, The another name of that is called two-level VSI. Why it is called two-level? Actually, this level is decided so in case of two level, you generally have what are the possible states? This is true for even so because of this, it is called two-level inverter. So somebody can always ask, can we have a zero state? But in the topology, what we are using in three-phase half bridge allows only two levels of pole voltages for all the three phases. So let's say if we take one of the phases, so S4 is always complement of S1. So when S1 is on, so we did not have any provision to connect the R to the midpoint. So if we can do that, we can get three levels of pole voltages. So that's how this inquiry. So let us talk about if we can have three levels, we can have more than three levels as well. So let us see. Let's say we have n levels of DC link voltages available to us. Then we can connect the pole to any of these voltages. So this how you get what is the use of such a thing, if you want to go for multi-level, definitely there is a increase in the number of levels of pole voltages, but what is the use of these things? Maybe let us quickly see some of the waveforms. It will help us to understand this. So this is a two level, so if you see the pole voltage of this kind of topology, so it will vary from but let's say if we have the three level or one more level added to two level, that is zero state, then if you see we can have 1, 0 and minus 1, that we can generally call as VDC by 2, 0 and minus VDC by 2. And if we go for still higher level, we get a pole voltage as in the figure. So definitely you can make out, we are as you are increasing the levels of the pole voltages, we are almost approaching sine wave in the pole voltage itself, and that is our desired state as well. We want a AC out of this inverter. So if the simple switching helps us to get these waveforms, the number of level helps us to get nearly sinusoidal waveform in the pole voltage level, it is fantastic. So let us see, what are the advantages this kind of multi-level configuration. So why multi-level converters? So this is a staircase waveform quality reduces. So what we want is, the lesser and less staircase. So if you, the more the level, the lesser the distortion. Let's say if you are operating for some n voltage, DC link voltage, if you have more number of switches, the stress across each switch will be less. Secondly, the quality of current will be improved. That is understood. So why the quality of current is improved? Because the quality of voltage also has improved. Secondly, if you see that, as you increase the number of levels, it means that let's say you can work at lower switching frequency now. So earlier, let's say you are working at 10 kilohertz for a 2-level inverter. When you go for 5-level inverter, roughly you can reduce the switching frequency to 2 kilohertz for the similar kind of output waveform, because you are now switching more levels. In 2-level you have to do the same thing in the next cycle. The level is shifted only in the next cycle, but here in multi-level converter you are shifting within the same cycle. So there's advantages like the quality of output voltage waveform is improved, quality of current definitely will improve because of the improvement in voltage. Switching frequency, actually if you are operating at same switching frequency, let's say if you are operating a 2-level converter at 10 kilohertz and you are operating the 3-level converter also at 10 kilohertz. And if you want to compare the performance, actually you have increased the switching frequency inherently by 2 times. This can be a way of comparison. So what is the catch? You are getting everything very nice things in multi-level, good voltage, good current, less voltage stress across the switches. So let's say for a 2-level converter, so you have to create, if you go for 3-level converter, you have to create 2 DC buses. And you have to regulate these 2 DC buses. So you need 2 diode rectifiers. So 2 diode rectifiers, and if they can be isolated is always good. So this level of complexity increases. And if you use a common DC link for so you need to have a separate DC link. So again review our understanding. So basically this is the waveform typically we get for a 2-level inverter. This we have a 3-level inverter. Since you have 3 switches, there was 3 switch locations, and you give for multi levels. So this is the pole voltage waveform. Basically we have 3 types of multi-level converter: cascaded multi-level converter, diode clamped multi-level converter, and flank capacitor clamped. So we will just look at this classification briefly. So this is the configuration of cascaded multi-level. So basically cascaded is, It's also known as multi-cell. So you can see that it's a single phase half bridge inverter. The configuration very similar to that. So if you connect the output of one cell to the input of another, you can create increased voltage level in a series fashion. So if we connect them in series, will it solve the purpose? See, our desired output is a sinusoidal waveform. So even though if we connect in series, the output voltage what we want is sinusoidal. So if we connect few cells in series, we have to switch them such that our desired output voltage is obtained. So let's see how we get it. So this will be the waveform of first cell, second cell, nth cell. So they will be switched in this kind of fashion. So if you add 1 plus 2 plus n, here is waveform. So this is a sinusoidal output voltage by connecting different cells in series. It has again the same disadvantage what we have mentioned earlier. This configuration requires you to have lot of DC sources, and in this case actually they have to be isolated. How to get them? So you need to have a bank of power supplies only for this purpose. But there is a big advantage also. Let's say there is a fault in one of the cells. So if there is a fault in this cell, it can be shorted. So this can be, so you may get a slightly reduced voltage, but still the inverter will keep working in the application. So it's a from reliability point of view, this kind of configuration is preferred, even though there is a complexity in the number of switches and all that. So going forward, let us see, the second type of multi-level converter. It's called diode clamped or neutral clamped multi-level converter. So this is, two level. This is so you get the middle and connect your four switches, 1, 2, 3, 4, and they are connected by means of these diodes. That's why the name is, diode clamped multi-level converter. So how this configuration is obtained? So actually initially we thought of connecting this center point to the center tape. So what they do, let's say, this is a circuit of diode clamped 3-level inverter. So this is a very famous configuration, and most of the high power what we have from ABB or Siemens, all are 3-level. They don't work on 2-level anymore. So here S3 is complement of S1, S4 is complement of S2. So actually when S1 and S2 are kind of switching together, and S3, S4 are anyway complement of those things, so they will be again will be same. Then it's reduced to a two-level converter. So we will study the diode clamped in detail after some time. So the third type is called flying capacitor. So instead of diodes, if we use capacitor clamp, also we can have a multi-level converter. But this topology is not used much uh, in industry. Industry actually we use diode clamp. So this, if you see these two and these two, these are like two level converters, DC link VDC by 2. So in total we have 27 states, out of which 4 each belongs to 2 level. Out of 12, 6 is root 3 VDC 2 level. Again, this we have 3 0 states. So basically these are the 27 vectors. So basically this is the space vector diagram of a diode clamped 3-level inverter. So if we see them together, when so basically now if you have any switching vector, you can possibility earlier in 2-level you only have this 1, 2, 3, 4, 5, 6. Now we have lot of active vectors spread all around the hexagon. So when you do space vector, you have lot of possibilities of applying active vectors, and therefore the voltage stress is less and you get number of levels more in the output. So another way of looking at it, it has six hexagons. So actually we also, so for switching this inverter, we can have two techniques. You can either use space vector or you can use sine PWM. So doing space vector for a three-level converter is quite complex, but it will give benefit as you've seen in terms of output voltage. But when you go for sine triangle, again the implementation is not so simple because now you have. So we generally apply when we do sine triangle PWM, we do. So we have to apply two triangles. So one triangle for the inverter what we have from 0 to VDC by 2, and another inverter from VDC by 2 to VDC. It can be read from literature. The more important was the space vector diagram. So I think let us wind up the multi-level converter part. So this I want to say that multi-level is a specialized field. So we have seen that just by going from 2 level to 3 level, we have seen that the number of vectors increased from 8 to 27. And so it will be 5 raised to 3, that is 125 vectors. So it's a very complex field, and you can see that a lot of people are doing research here. So now let us try to see our last topic, that is first to voltage source converter. We can have current source inverters, but so current source inverters are very rarely used. So current source inverters basically, so one topology we can see is current source inverter topology. It's used for running a salient pole or cylindrical salient pole synchronous machine. So wound field synchronous machine. So if you use thyristors, by controlling the alpha firing, the output voltage can be controlled. And V0 plus inductor, this is inductor. So this variable rectifier plus a inductor create variable current source. So basically current is the input to this part, which is called. So what this inverter does, so we in a voltage source converter the input is DC voltage, but this kind of topology the input is current. Only give currents to the motor. So rectifier needs line commutation, and this needs so this kind of topology cannot be used. See, this kind of topology is used for running synchronous motor because it can provide a load power factor. So this so if we want to use current source for induction machine, we cannot use thyristors. Instead, we have to go for a device which is popularly known as GTO. So GTO is basically a high power device which can be turned on and turned off. It has a gate power loss, but still, actually, for some application, if you want to use, you have to make the CSI configuration using GTO for a induction motor application. So I think I will like to wrap up today's session. Uh, so we have seen, the types of multi-level converters. Why there is a need for going to multi-level converters? You have various advantages of multi-level converters, especially if you're looking for very high applications. So we use cascaded multi-level for HVDC application. We use 3-level diode clamp converter for all the motor drives. Actually, if you get from ABB or Siemens or any big drives company. But when you go for multi-level converter, this complicated is number of features, and you have to know how to handle them. So we have just understood, spent quite some time for understanding the theory behind 3-level diode clamp converter. We have seen that, there's a immense increase in the number of switching states just from going to level to 3 level, from 8 to 27, and the kind of flexibility that it gives us, And actually, we have also, current source inverters. So current source inverters are is used only in very high power applications where you cannot take the IGBT to that level. and current level. So those kind of applications we use current source inverters. Again, the applications of so I want to wrap today's session from my point of view. Now what we can do, we can use the rest of the time. We have almost half an hour remaining, so we can take up questions, and if you have any queries regarding the assignment or quiz or any of the three sessions, we can take it up. So I think we are in last 5 minutes of the session. So let us again wind up. Thank you all of you for attending the sessions. I hope things have gone well. You might have learned something which will be useful. So actually, I want to share with you some of the books what we referred. You know, actually, if you're interested in PWM techniques, so there is a book by Holmes and Integrated Pulse with Modulation of Power Converters. If somebody is interested in high, so by Bin, fantastic book. So anyway, so these are some of the books you should read actually to understand the depths of our pulse width modulation techniques. Um, so, so we have covered this last 3 sessions is inverters. Actually, the topic of our discussion was inverters, and I hope we are able to touch the topic quite well. So we started with single phase inverters. We have gone to 3 phase inverters. See, in the textbooks conventionally available in UG literature, we all talk about 120-degree mode of condension, 180-degree mode of condension. But no, things have changed. Now we use sine PWM technique and space vector PWM technique. And I hope I was able to give a basics of these things and how these techniques help us to improve waveform, the torque waveform if it's a motor application. And look at how the DC link is output voltage in each of these techniques. So there is a limitation of the output voltage quality in a two-level converter. So people thought, why not improve the levels or increase the levels such that we get a very good voltage waveform, almost sinusoidal waveform at the pole voltage level itself. It has led to the evolution of multi-level converters. But understanding multi-level converter is not so easy. And the space vector diagram. Can you, if you want a space vector modulation for a three-level converter, so which switch to select, how to calculate the time for which each switching state will be applied is quite complex. Actually, you can refer to so these two professors work very deeply in PWM techniques, especially Professor Narayanan works on PWM techniques and Professor Gopakumar works on multi-level converter. So he has done enormous work in this area, both of these professors. So if you visit their website and see the literature, if you want to understand, deeper level of understanding, places and personally interact with them. So again for joining this session and listening to me. So this was my first QE lecture series, so it may not have turned out to be so well, but I hope I was able to give a gist of it and what are the trends, whether inverter topology or technology is evolving. So please drop me email if you have some queries related to this topic. I can answer all of them. So thank you.